Hello everyone. In previous lecture we have seen this derivation of unit step response for second order system. Okay, and that equation was very important. So previously we have seen all this derivation. We have taken a CS, which is system function into RS, that is a step input, that is 1 upon S. We have solved for this partial fraction. We have converted that into time domain with the help of inverse Laplace, and with the help of some trigonometry formulas, finally we have got this equation, that is CS is equal to 1 minus e raised to minus zeta omega nt divided by under root 1 minus zeta square into sine in bracket omega dt plus tan inverse under root 1 minus zeta square divided by zeta. So what is the significance of this equation that we have to see in today's lecture? Okay, because if you see this equation, your system's response will be carried out with the help of this equation only. Okay, and there are different time domain specification or parameters that we have to see in this lecture, so which are calculated with the help of this equation only. So there is no any other equation for that, and for us understanding of that is very important. Okay, so that's why we have seen how this equation is derived. Okay, if I directly tell you the equation like this, then you will not understand. So that's why I have explained how this equation is derived. Okay, and I think it is simple. Just you must know the different mathematical concepts that you have seen in mathematics, like M2 and M3. Okay, subjects. So let's move forward with that actual time response specifications or the parameters that I was talking about. So this is the time response specification, complete response, we can say complete time response specification for second order system for a unit step. Okay, now this response is subjected to this equation only for. Okay, so if you look this equation, okay, you will get this if you look this diagram, this diagram is obtained from this equation only. Okay, so that's why this equation is very important, and as per this diagram and the different parameters, you will get the values of the time domain specification like TR, TP, then TD and TS. Okay, so this is a time response specification for second order system. Let us study this diagram, which is very simple. So initially, if you look at this diagram, okay, and what is the basic understanding from this diagram? Okay, let us discuss that basic understanding first. So here you will get two axes. This is a time domain, time axis. Of course it is time domain specification, so that's why it is time axis, which is x-axis, and if you see, this is a y-axis, that is a CT. So simply by looking this diagram, our simple conclusion is that this is output's response in a time domain. So how the output is going to change for a given step input, see here, for a given unit step, how this output will change with respect to time. This is nothing but the basic understanding from this diagram. So this is the CT, again I am repeating, this is the output with respect to time, and this is the input, that is one unit step, and this is the response of the system. Okay, so by looking this diagram, our final conclusion is that whenever I apply the unit step input in a time domain, first of all output will rise like this, then I will get here overshoot or peak, here positive peak, then I will get negative peak, then again I will give positive peak, again I will get this negative peak like this, and this is called as oscillations. And after some time my output or my system's output tries to become stable for a given input. Okay, so practically you will get the response like this. Okay, ideally I should get one output like this. If I am going to apply the step input like this, I should get the output like this only. Okay, this is, we are talking about ideal condition, but practically we are getting some oscillations like this. Okay, of course there is a damping in the system, so that's why system will try to become a stable. Okay, so again here ideally the system will try to become a 1, but there is some error in the system, and that is called a steady state error that we will see afterwards. And here that will, the output that we will get in 2% band only. Okay, so it is much accurate. It is not 100% accurate, but it is much accurate. It will not oscillate above, or it will not go outside this 2% band. Okay, so this is the simple observation from this diagram. Here if we apply the unit step here, the system will increase slowly, then it will give some positive peaks, it will give some negative peaks, and after that it will try to become a stable. Now if you see this diagram in deep, there are certain parameters and there are certain values that we have to study, and these are called as a time response specification of any system. Okay, so if you see this equation plays a more important or most important role when we calculate these parameters like TR, TP, TS and TD. Okay, now see here what is TR here. Okay, see what is a TR. From this 0 up to this value there is TR. Okay, so we will see the definition. Just see where it is located. From this point it is located. Okay, so this much time is TR, which is called as a rise time. See just where, from where it is calculated. Then another important part is TD, that is time delay. So if you see here where it is located something from 0.5, value of 0.5, and from 0 to 0.5. Okay, so if you see this TP, that is first peak, it is taken from the first overshoot. If you see this first overshoot amplitude, as highest amplitude is somewhere here. So from this point towards this, from this 0 to towards this maximum point, this TP or peak time is calculated. It is all about this TR, TP and TD. And somewhere here, when system's oscillations becomes less than 2%, and after that system tries to obtain or get a steady state output. Up to this is somewhere called as settling time or a TS. Okay, so this is from this 0 to up to this point, this is a TS. From 0 to towards this point, this is a TD. Then from 0 to towards this point, that is a TR. And up to this peak point, from this 0, it is TP. Okay, so let us understand in deep what do you mean by these parameters one by one. Okay, and if you see previous papers, then most of the examples are asked on this calculation of this TR, TP, TD, TS. Okay, so they will not ask you the derivations. Okay, they may ask, but there is a less chances, but definitely there will be examples on calculating the TR, TP, TD, TS. So you must know at least the equations of that. Okay, and if you get a time, we will see that derivation. It is again very simple. You can refer that Bharapte book. In that it is given, but this chapter is huge, so we don't have that much of a time. If we get a time, don't worry about that, we will discuss about that, but it is related to this equation only. Okay, so that's why take this as a homework and see how this is calculated. So right now I will just discuss the basics about this, and I will just denote direct equation related to that, and that is your homework, that you have to calculate these parameters. 3 to 4 parameters are there with the help of this equation. Okay, so that's why I have taken this equation in deep, so that you can calculate these parameters at your own. Otherwise if we get a time, we will see how to derive these parameters, but right now I will explain the definition of this, so that you can understand that, and after that you can derive the equation for this. So let us see first time response specification, that is a delay time. So if you see this delay time, it is denoted by TD. Okay, so what is basically TD here? It is time required for the response to reach 50% of the final value in the first attempt. Okay, now here in this case we have applied unit step. So what is our final value? That is 1. So what is the 50% of a final value? That is 0.5. So of course the definition tells us that it is time required for the response to reach 50% of the final value of the first attempt. Here final value is 1, so 50% is 0.5. So it is a time to reach our output to its final value, to its 50% of a final value when the input is applied. Means from 0 to time required to get the system's output to the 50% of a final value. So in this case it is 0.5. That time is called as a delay time. So here, see here, it is started from 0, okay, and it is up to this point, means what? Up to 0.5 value of a final value, that is, or 50% of a final value, that is a 0.5. Okay, so here this time delay is defined like this. Okay, and in this here in this slide you will get the equation like this, that is TD is denoted by 1 plus 0.7 zeta divided by omega n. Now how this value is calculated, let me give you idea about this. See, we are discussing this in a time domain, yes or no? So we have to put the value of this TD, okay, in upcoming equations, but you must know how it is calculated. Okay, now in this case how to calculate, let me explain this. Here the equation is given over here. Okay, so here T is equal to TD you have to put in this equation. You have to put T is equal to TD, because the delay time is the time required for the response to reach 50% of value. So just I am giving you idea so that you can calculate afterwards if you want that. So just make a note of that, okay, and consider that is your assignment, okay, related to this chapter or this unit. Okay, so what is the TD? TD is time required for response to reach the 50% of a value. Okay, so in this case, if I take this equation, why I am taking this equation? Because this is the time domain specification, okay, or we can say this is the derivation of a unit step response for second order system, and we are discussing the time response of a second order system. So that's why this equation plays a very important role while calculating this time domain specifications. Okay, so let us see this equation. Here TD we have to calculate. So if you replace T with TD, you should get 50% of a value. So here you have to put CT is equal to 1/2 or a 0.5. Okay, so I think you got this, and after that just make the arrangement and calculate that TD. Okay, and you will get the equation like this, that is 1 plus 0.7 into zeta divided by omega n. Again I will repeat, TD is nothing but time required to get the response to reach 50% of a final value. So here if you put T is equal to TD in this equation, CT will be 1/2 or 0.5 in this case. Solve this equation, and after that you will get the equation like TD. Okay, don't worry, if you get a time we will see more about this, but take this as your assignment. Okay, it is clearly given in a Bharapte book. You can refer that or any book and just take that as your assignment. Okay, so TD is equal to 1 plus 0.7 zeta divided by omega n. So I think you got the definition of a delay time. Let's take the next value, that is rise time or a TR. So rise time is given by TR. So it is basically time required for the response to rise from 10% to 90% of a final value for overdamped system. Okay, but if you consider the underdamped system, then it is time required from 0 to 100%. Okay, so it is time required to response to for the response to rise from 10% to 90% for overdamped. See here carefully, for overdamped system, and it is from 0 to 100% for underdamped system. Okay, so here in this case, here in our case, TR will be what? It will be from 0 to this 100%. Okay, So this is your TR, and if you solve this equation again, TR, then you will get the equation like this: pi minus beta divided by omega d. Okay, so where omega d is equal to omega n into under root 1 minus zeta square, where beta is equal to tan inverse under root 1 minus zeta square divided by zeta. Okay, so explanation of this is again given in a book. Okay, so you can refer that. You can derive the equation for this. Okay, with the help of again this equation. So this we have seen. So if you see the next parameter, that is peak overshoot. So the maximum overshoot is the maximum peak value of the response curve measured from the unity. See here, what do you mean by overshoot? The maximum overshoot is the maximum peak value of the response curve measured from the unity. Okay, so here if you see the maximum overshoot amplitude, it is calculated from the maximum overshoot. Okay, maximum overshoot means what? The overshoot which is having the highest amplitude. So here this is also called as overshoot, this is also called as overshoot, and this is also called as overshoot. But out of this 3 or 4, which is maximum? So this is the maximum. So how to calculate the amplitude of this maximum overshoot? Just measure it from unity to peak value, okay, or this highest value. So this is amplitude of a maximum overshoot. Again I am repeating here. What do you mean by overshoot? Overshoot is nothing but something, the value, something that is getting from, we are getting from this one value or above this one value. Okay, so if you see, this is also called as overshoot, this is also called as overshoot, this is overshoot, this also called as overshoot. But which is highest overshoot? This is highest overshoot because its amplitude is high. And how to calculate the amplitude? You have to measure it from this 1 towards this maximum value. So we have to locate here somewhere here, and that will be the amplitude of maximum overshoot. So the maximum overshoot is the maximum peak value of the response curve measured from the unity. Okay, and it is therefore the largest error between the input and output during the transient period. Okay, so what do you mean by transient period? That we have seen already. So after this you will get a steady state response, and before that whatever the response that we are getting from 0, that is called as a transient response. So I can call this period from this point towards this point, this is called as a transient response. Okay, and in that transient response, this maximum overshoot will give you the error, and that will be the maximum error, because here whatever the value which will be the greater than 1, that will be considered as a error here. So it may be positive or it may be negative, but here we are talking about the positive only. So this maximum overshoot will give you a maximum error because it is having a maximum amplitude over this 1. Okay, so that's why it will give a maximum error over here. Okay, so that's why it is written over here, that is, it is therefore the largest error between input and output during the transient period only. That is very important. Okay, so how it is given? It is given by percent maximum peak overshoot, that is MP. So percent peak overshoot, that is percent MP, is equal to e raised to minus zeta pi divided by under root 1 minus zeta square into 100. Okay, so it is written in terms of a percentage. That is very important. So I think you got the idea about this, and let's move towards the last point, that is peak time. Okay, so again it is related to this peak overshoot. It is time required for the response to reach the first peak. Okay, now what do you mean by first peak? Here this is called as a first peak. Because why it is called as first peak? Because from this point the response, the system's output response will cross this unity or output 1, and it will reach, or it will get, or it will acquire some highest value. Okay, and this is called as a first peak. So if you see, this is called as second peak, this is called as third peak, and so on. But if you see, this is our first peak. Okay, and the time required from this 0 to this first peak or a maximum value, that is called as a TP. I think you got the idea about this. Okay, because we are talking about this first peak. Okay, so what do you mean by this peak time, TP? It is the time required for the response to reach the first peak. and it is denoted by TP, which is equal to pi divided by omega t. Okay, so I think you got the idea about this. I think one more parameter is remaining here, that is the settling time. Don't worry, we will see that. But if you see this peak time, it is the time required for the response to reach the first peak, that is TP is equal to pi divided by omega d. Okay, now if you see the settling time, that is a TS, it is time required for the response curve to reach and stay within a specified percentage, usually 2% or 5% of the final value. Okay, let me read this again. It is time required for the time response curve to reach and stay within a specified percent, usually 2% or 5% of the final value. Okay, now this settling time is a total time after which your steady state response will start. Okay, so if you see here in this case, from 0 to TS, if you see this response, this is called as a settling time, because up to TS system was giving you some oscillations and some undershoots and overshoot and some we can say instability over here, and after that system tries to acquire that final value which is nearly equal to 1, but practically we will not get that 1, so it will again remain in a 2% band or 2 to 5% band. But standard, if you see the standards, just consider that as 2% band. Okay, so whatever the time that you will require from starting 0 towards settling that to within a 2% band, that is called as a settling time. Okay, so it is time when we apply step input to that system, second order system, and after that that settling time you will get system's output within this 2% band. Now one important thing I want to mention here is that here, while designing any control system, second order system, and if you see this band, 2% band, it will be better for you, okay, if you get this band much lesser. Means what? It is written over here that is it must be from 2% to 5%, that definition of a settling time, but it will be better for you if you get this percentage, less percentage. Okay, obviously you will not get 0% accuracy here, 0% band here or 100% accuracy here, but it will be somewhere in 2 to 5%. If it is less than 2%, then it is very good, like 1% or 5% band. So if you go on increasing this percentage, go on decreasing this percentage, the accuracy will be more, and if you go on increasing this percentage, the accuracy will be less. Okay, so that's why it is preferred that this percentage will be as less as possible. Okay, so that is one important point that I want to add here. Okay, now if you see this settling time, okay, so obviously it will be greater than all the parameters like TR, TP, TD. Okay, so in other words, I can say that this TR, TP and TD are a parts of a TS, we can say that. Okay, but while designing this TS is very important, because this TS will give you how quickly system will acquire its desired value. Okay, so again here I want to add one another point is that while designing a system, please see that this settling time will be or must be as less as possible. If this TS is less, then system will acquire its desired output very fast or fastly, and if this TS is increased or it will be having a higher value, and then the system's response will be slow, means it will take more time to acquire its desired value. Okay, so that is the important point here I want to add. Okay, now if you see here if you see here settling time, that is TS, so it is time required for the response curve to reach and stay within a specified percentage, that is 2% to 5%, okay, of a final value, and generally consider that as a T's value here as a, I think we have seen that in first order systems analysis, so it should be like 4. Okay, so TS is considered as a 4T here, and here it is denoted by 4 divided by zeta omega n. Okay, so 40 is a standard value which is considered for settling time. Okay, if you see that graph that we have seen in first order system analysis, you can refer that. Okay, so over 40 we are just considering the value we are getting as a in a 2% band or in a 2 to 5% band. Okay, so this is all about the parameters, systems parameters that we have studied now. Okay, so if you see here, previously we have seen this equation. From this equation we have got this time response specification, standard response, and inside that see what we have done, that we have calculated TR, we have calculated TP, we have seen definition of a TD, then settling time, and after the settling time you will get the steady state response. Okay, so of course there will be a error that we will see in upcoming lectures, don't worry about this. Okay, so what we have seen here, let's summarize this. So first of all we have to apply some step input. So here in this case it is having an amplitude as of 1. So ideally I should get output like this also, but practically we will not get, because there are some system components which will oppose to this, and system will try to oscillate, and after that it will try to get the final value. So the time period in which system tries to oscillate, that is called as transient response, and after transient response system tries to get the desired value, and that is called as steady state response. Okay, so here whenever we apply the input and we observe the output, the time required by the system to get a 50% of a final value, that is called as a delay time. Time required for the system to get 10% to 90%, or in some cases 0% to 100%, that time is called as a rise time. Okay, so whenever system, after giving the input, whenever system gives you output, it will not stable over here, that desired output, it will go above that, and that is called as overshoot. After that it will give you undershoot, again it will give overshoot, undershoot, and as it is damped system, okay, though it is under damped, it is damped, that's why this amplitude will become smaller and smaller and smaller. Okay, but the highest peak is called as maximum overshoot, or peak overshoot we can say, and the time after which we will get this maximum peak of this overshoot, that is called as peak value or TP, and after some time this overshoot and undershoot amplitude tries to become small, or due to that damping, system's response tries to become desired response. Okay, and the time after which this response comes in 2% error band. Okay, so here in this case it is considered as a 0.98 to 1.02. if you calculate the 2% of this one, you will get this value. So if it is a minus error, then it is a 0.98, and if it is plus error, it is plus 1.02. okay, so here in this case it is 2% band, and it will acquire 2% value after settling time, which is called as TS. Okay, and in short, TR, TP and TD, these are the settling parameters we can say. So it comes under this point only, that is TS. So we have seen the definition of this and some equation of this. Okay, so in exam they will give you a system function, and with the help of that you have to just calculate this delay time, rise time, peak overshoot and peak time. Okay, and settling time. Okay, so these 4 to 5 parameters you have to calculate. Okay, in sometimes they may ask you the derivation of this, but most of the times, more than 90% I can say, they will ask you the calculation about this. They will give you a system transfer function, and just they will give the this parameter 4 to 5, and each parameter will be having 2 marks. So 8 mark question will be there. Okay, and this derivation that you have to do, that is your homework or assignment for this unit. Okay, after if you get a time, you will see that, but this is your homework. It is given in Bharati book. I will repeat this if you get a time. but this is your homework. You have to derive this parameters, that is TD, then TR, MP, TP, TS. Okay, so in short, let's see the equation. TD is given by 1 plus 0.7 zeta divided by omega n, then TR is equal to pi minus beta divided by omega d, where omega d, you know that omega d is omega n into under root 1 minus zeta square. So beta is equal to tan inverse under root 1 minus zeta square divided by zeta. Then MP is equal to e raised to minus zeta pi divided by under root 1 minus zeta square into 100. It is calculated in percentage. Then TP, that is peak time, is TP is equal to pi divided by omega d. And last parameter is settling time, where 4t is considered as for a standard settling time, after which we will get a steady state response. So 4t is considered for that. So by this 4t, if you put that equation in this value in that equation, you will get the 4 divided by zeta omega n. Okay, so just note down all these parameters and its equation, and with the help of this we will solve some examples based upon this, how it is solved. Okay, so remaining time you have to utilize for your assignment. You have to just calculate you have to just derive this TS, TD and all these things. Okay, so thank you very much. We will stop here. So in next lecture we will see the examples on this. Okay, thank you.